Hello and welcome back to Introduction to Number Theory. In this video, I would like to discuss the geometric sequence modular prime number. So let's put P to be an arbitrary prime number. We occasionally denote the set of prime numbers as pretty P, and take A to be a non-zero remainder modulo P, or just an integer which is not divisible by P. It doesn't really matter, because what we will do is we will study the sequence 1, A square, A cube, A to the power 4, 5, 6, and so on. So what can we say about this sequence? Of course, we will study it modulo P, which means that all these integers we bring to their remainders modulo P. And this sequence consists of remainders. So we can assume that all its elements are less than P and greater or equal to 0. Okay, so what can we say about this sequence? Well, of course, it is an infinite sequence, while all the elements can have only finite set of values. So sooner or later, they will repeat. And after one of the elements repeats, the sequence will become cyclic. However, we know from our small theorem, which states that when we get to A to the power of P minus 1, then this will be congruent to 1 modulo P, which in the sense of considering all this modulo P means that simply we have remainder 1 at this place of the sequence. And after we have 1, then the next element of the sequence will be A, because the next element is obtained from the previous element by multiplying by A. So A, and then A square, and so on. So at least it is cyclic with length of the period equal to, well, P minus 1. However, can we be sure that within these elements, all of them are different? Well, of course not. We already know that since there is power P minus 1, when raised to which A is congruent to 1, then there is the least positive integer such power, which we call order of A. So put K equal to order of A modulo P. So we know that A to the power of K is congruent to 1 modulo P, and this is the least positive integer with such property. And if, well, it can occur that K is equal to P minus 1. It is possible. But K is for sure not greater than P minus 1. So maybe one of these elements is also congruent to 1 modulo P. If it is so, then our sequence looks like 1A, A square, and so on, A to the power of K, which is the first element of this sequence, that's congruent to 1, except for the beginning of the sequence. It's congruent to 1. And after this, A repeats, A square repeats, and so on. And then when we get to a to the power of 2k, it is also congruent to 1. Well, congruence modulo p, of course. And so on, and a square, and so on. And of course, we understand that now this is the repeating part of the sequence. So this is the same as the next part, is the same as the next part, and so on. So it consists of k elements, and k elements here, and k elements here, and so on. Can we be sure that all of these elements are distinct? Well, this time the answer is yes, indeed. If some of these, say a to the power of x, is congruent to a to the power of y modulo p, where x and y are both less than k, why less? Because a to the power of k is right over here, so all these powers of a are less than k. Then in this case, we understand that there exists remainder which is such that multiplied by a, let's call this remainder b, such that ab is congruent to 1 modulo p. It's an inverse of a. And multiplying by b, well, let's say that x is less than y, and then multiply all this by b to the power of x, well, multiplying by b to the power of x, we have 1 is congruent to a to the power of y minus x modulo p, and we understand that, well, it's quite weird because this power is surely positive and less than k at the same time. So we have a contradiction with the assumption that k is the order of a. Finally, all these elements are distinct modulo p.